There is a chip that was never supposed to exist. Not because the physics was impossible, not because the engineering was beyond human capability, but because the most powerful government on Earth decided, publicly, legally, with the full weight of export control law, that this chip would never be manufactured. They cut off the factory. They cut off the software. They cut off the tools. They cut off the materials. And they said, that is the ceiling. You will not build the future without our permission. And then Huawei folded the chip. Not literally, but functionally. Instead of making the transistors smaller, which requires the machines they were banned from buying, they stacked them, folded the logic vertically, and achieved a transistor density of 238 million per square millimeter. That number matters, because that is the same density that TSMC achieves with its 3-nanometer process. The same density, without the machines, without the tools, without permission. This is happening right now, today. The chip launches this fall. It was presented at IEEE by Huawei's semiconductor chief, and it is not a prototype. It is not a roadmap slide. It is going into a phone that you will be able to hold in your hand in a matter of weeks. If you want to understand how the single most important technology monopoly of the 21st century just got broken from the inside, hit subscribe. It genuinely helps this channel, and the next few years are going to produce one story like this after another. Let's get into it. To understand why this chip is so monumental, you need to understand the rule that governed the entire semiconductor industry for 60 years, and you need to understand why breaking that rule was considered impossible. The rule is called Moore's Law, and for 6 decades it was not just an observation, it was a religion, a self-fulfilling prophecy that dictated how every chip company on Earth spent its research budget, planned its roadmaps, and justified its billion-dollar capital expenditures. Moore's Law says this: roughly every 2 years, the number of transistors you can fit on a chip doubles. Not because someone invents a new architecture, not because someone designs a clever new circuit, but because the manufacturing process shrinks. The transistors get physically smaller, and when they get smaller, you fit more of them in the same area. And here is the critical part. Making transistors smaller requires better lithography. Better lithography means shorter wavelengths of light. And the shortest wavelength that the industry has ever achieved is extreme ultraviolet, 13.5 nanometers, EUV, made by one company, ASML, in the Netherlands, and exported only to countries that the United States approves. So the pipeline looked like this. You want a more powerful chip? You need more transistors. More transistors means a smaller process node. A smaller process node means EUV lithography. EUV means ASML. And ASML means Western permission. That was the architecture of the entire global semiconductor industry. Not a conspiracy, not a secret agreement, just a supply chain that happened to have one choke point, controlled by one coalition, with one kill switch. And for Huawei, that kill switch was flipped in 2020. The United States issued a series of export controls that progressively cut Huawei off from TSMC, the foundry that manufactured its chips. From EUV lithography, from advanced EDA design tools made by Cadence and Synopsys, from American-made testing equipment, from Japanese photoresists, layer by layer, the access was revoked. The last Kirin chip manufactured by TSMC was the Kirin 9000 in 2020. After that, nothing. The assumption, stated openly in policy papers, in think tank reports, in congressional hearings, was that Huawei's semiconductor division was finished, that without access to advanced manufacturing, they could not compete, that within 3 years, they would be irrelevant. 3 years later, in 2023, the Kirin 9000s appeared in the Huawei Mate 60 Pro, manufactured by SMIC, using deep ultraviolet lithography, the older technology, with a technique called multi-patterning. It was a 7-nanometer class chip, not cutting edge, but functional, and it proved something that the sanctions architecture assumed was impossible, that China could manufacture advanced chips without EUV. But the 9000s was a survival move, a proof of concept. The transistor density was roughly 153 million per square millimeter, competitive with 5-nanometer chips from 3 years prior. Respectable, but not leading edge. The West adjusted its assessment. They can build chips, but they will always be 2 generations behind. The gap is structural, permanent. You cannot match TSMC without the same tools. That assessment held. Right up until Huawei decided that the gap was not in the tools, The gap was in the rule. So here is the question everyone asked, and it was a fair question. If you cannot shrink the transistors because you do not have EUV lithography, how do you get more transistors on the same area of silicon? Is there no other way? And the answer technically has always existed. There is another way. It is called three-dimensional integration. Stacking transistor layers vertically instead of packing them horizontally. And the semiconductor industry has known about it for over 20 years. But they did not do it. And the reasons they did not do it are specific, physical, and instructive. Reason 1. Heat. When you stack transistors vertically, the layers on the bottom have no way to shed heat. In a flat chip, heat radiates upward and outward through the silicon substrate and into a heatsink. In a stacked chip, the heat from the upper layers cooks the lower layers. The thermal density becomes catastrophic. You can stack 2 layers, maybe 3, but beyond that, the chip throttles itself into uselessness. Reason 2. Alignment. When you stack layers, you need to connect them vertically with microscopic conductive pillars called through-silicon vias. Those vias need to align across layers with tolerances measured in tens of nanometers. If you are off by even a few nanometers, the connection fails. And when you are stacking logic circuits, not memory, not passive interposers, but active logic with billions of connections, the alignment tolerance becomes almost impossible. Reason 3. Yield. In a flat chip, if one transistor fails, you lose that transistor. In a stacked chip, if one via fails, you lose the entire vertical stack. The defect tolerance drops exponentially with each added layer. And when your process node is already constrained, when you are using DUV multi-patterning instead of EUV, your base defect rate is already higher than the leading edge. Stacking on top of a higher defect rate makes the yield collapse. Reason 4. Design tools. The entire EDA software ecosystem, Cadence, Synopsys, Siemens EDA, was built for two-dimensional design, the routing algorithms, the thermal simulation, the timing closure. All of it assumes a flat plane. Designing in 3 dimensions requires entirely new tool flows, and those tools do not exist yet in any mature form. So the industry looked at 3D stacking and said, too hot, too hard, too expensive, too risky. The dismissive framing was more than more, a catch-all phrase for niche academic research that would never ship in a consumer product. It was the semiconductor equivalent of a science fair project. Interesting, impractical, not the way you build a phone chip. And here's the trap this created. Because the entire industry optimized for shrinking, the only way to compete was to shrink. And the only way to shrink was EUV. And EUV was controlled by one coalition. So the entire industry, every company, every country, was locked into a single scaling path, a single technology tree. And the gatekeepers of that tree held the keys to the future of computing. Huawei had the motivation to find another path. The sanctions gave them that. But motivation alone does not solve thermal physics. Motivation does not fix via alignment. Motivation does not write new EDA tools. What motivation does is force you to ask a different question. And Huawei asked a different question. Here is the twist. And this is the part that changes everything. Huawei did not try to build a 3D stacked chip in the way the academic literature described. They did not try to stack identical logic layers on top of each other like a layer cake. That is the approach that fails thermally. That is the approach that kills yield. They folded the logic. And here is the critical distinction. In traditional 3D stacking, you build the same type of circuit on each layer and stack them. The heat problem is uniform. The alignment problem is uniform. The yield problem is uniform. Everything gets harder at the same rate. In logic folding, you separate the logic by function. You put the high heat, high frequency compute logic on the top layer, where it has direct thermal access to the heatsink. You put the memory interfaces, the I/O logic, the always-on control circuits on the lower layers, where they generate less heat and do not need to run as fast. You fold the chip like a book, not stacking identical pages, but folding different chapters into different positions based on their thermal and electrical requirements. Let me walk through the mechanism step by step. Step 1. Partition the design. Instead of designing the entire system on chip as a single flat layout, Huawei's engineers partition the logic into functional blocks. The high-performance CPU cores, the GPU compute units, the neural processing unit, the memory controllers, the I/O interfaces. Each block gets assigned to a layer based on its thermal profile and its interconnect requirements. Step 2. Fabricate each layer independently. Each functional block is manufactured on its own wafer, using the process node best suited to it. The high-performance logic uses SMIC's most advanced node, the multi-patterning DUV process. The I/O and control logic can use a mature, cheaper node. This is critical. You are not forcing every layer through the same expensive process. You are matching the process to the function. Step 3. Bond the layers face-to-face. Using hybrid bonding, a technique where copper-to-copper connections are made at the atomic level between two polished wafer surfaces, the layers are fused together. No solder bumps, no micro bumps. Direct metal-to-metal contact at the nanometer scale. This gives you via density that is orders of magnitude higher than traditional through-silicon vias, and it gives you alignment tolerances that are achievable because the bonding is done at the wafer level, not the chip level. Step 4. Thin and polish. After bonding, the top wafer is ground down to a thickness of a few micrometers. The excess silicon is removed. What remains is an ultra-thin layer of active transistors sitting directly on top of the layer below. The total stack height is still compatible with standard chip packaging. Step 5. Route vertically. The interconnections between layers are made through the hybrid bond interfaces. Because the bonding density is so high, thousands of connections per square millimeter, the vertical bandwidth is enormous. Data moves between layers almost as fast as it moves within a single flat layer. And here is the brilliant part. The 4 killers of traditional 3D stacking: heat, alignment, yield, design complexity. They do not get fixed, they get designed around. Heat is managed by putting the hot logic on top. Alignment is managed by wafer-level hybrid bonding instead of chip-level via drilling. Yield is managed by using different process nodes for different layers, so a defect in the I/O layer does not kill the compute layer. Design complexity is managed by partitioning the system into functional blocks that are designed independently and then assembled. The old weaknesses were properties of the wrong architecture. Change the architecture, and the walls become design constraints. The result: 238 million transistors per square millimeter, a 53.5% increase in density compared to the previous two-dimensional design on the same process node, a 41% improvement in performance core throughput, a 12.7% increase in maximum clock frequency, all without shrinking a single transistor, all without EUV lithography, all without ASML. Huawei presented this at IEEE ISCAS, one of the most prestigious circuit design conferences in the world. They called it the Tau scaling law. Tau, the Greek letter, and the name is deliberate, because Tau is not more. It is a different law, a different scaling principle. And it is Huawei's declaration that the 60-year monopoly on semiconductor scaling is over, that you do not need to shrink to advance. You can fold instead. But a conference paper is one thing. A shipping product is another. And this is where the story stops being a research breakthrough and becomes an industrial reality. The Kirin 2026 chip launches this fall. It is going into Huawei's next flagship device. He Tingbo, Huawei's semiconductor division chief, has publicly demonstrated the chip, not in a lab, not in a simulation, in a working device, running real workloads, in front of cameras. The specifications are concrete and verifiable. 238 million transistors per square millimeter, an 8-CU GPU, a 6-core NPU for AI inference, a 41% faster performance core compared to the previous generation, a 12.7% higher peak clock frequency, a 55% overall performance uplift compared to the Kirin 9000s. Let me ground that last number. The Kirin 9000s was a 7-nanometer class chip made with DUV multi-patterning. It was competitive with chips from 3 years prior. The Kirin 2026 is a 55% leap over that chip, in a single generation, without changing the underlying lithography. That is not a process node improvement. That is an architectural improvement. And architectural improvements compound differently than process improvements. They do not require new factories. They do not require new tools. They require design. And design is the one thing that sanctions cannot fully embargo. And the roadmap is public. Huawei has announced plans for 1.4 nanometer equivalent chips by 2031, not by shrinking to 1.4 nanometers, by continuing to refine logic folding, by adding layers, by improving the hybrid bond density, by optimizing the thermal stack. The Tau scaling law is not a one-time trick. It is a multi-year roadmap. Now zoom out to the national policy layer, because this is not one company's breakthrough. This is a national industrial strategy executing on every axis simultaneously. China's National Integrated Circuit Industry Investment Fund, the Big Fund, has deployed over 300 billion yuan across 3 phases into the semiconductor supply chain. Phase 3 alone targeted over $40 billion in new capital. SMIC, Huawei's manufacturing partner, has received billions in direct state investment to expand its advanced node capacity. The company is building new fabrication lines in Shanghai, Beijing, and Shenzhen specifically for multi-patterning DUV processes. The EDA tool gap is being addressed too. Huawei has been developing its own internal design tools since 2020. In 2024, the company announced that it had completed a domestic EDA toolchain capable of designing advanced chips without American software. It is not as mature as Cadence or Synopsys, but it works. And every chip designed on it is one more data point proving that the Western software monopoly is not permanent. And the talent pipeline is enormous. China graduates more electrical engineering and computer science PhDs per year than the United States, Europe, and Japan combined. Huawei alone employs over 110,000 researchers. The company spends over 20% of its annual revenue on R&D, putting it among the top 5 research spenders on planet Earth. The constraint was never talent. The constraint was access, and access is what the sanctions removed. And access is what Huawei rebuilt, painfully, expensively, but completely from the ground up. Every quarter, the yield improves. Every generation, the density climbs. Every year, the gap between the sanctioned path and the sanctioned against path narrows. This is not a sprint. This is an industrial ramp. And industrial ramps, once they start, have a momentum that is almost impossible to stop. But here is the honest part of this story. And I want to be straight with you, because this format does not do blind hype. 238 million transistors per square millimeter is competitive with TSMC's 3nm node. But TSMC is not standing still. TSMC is already ramping 2nm production. And TSMC's 2nm process uses gate-all-around transistor architecture, which is a fundamental structural change that gives it performance and power advantages that LogicFolding does not directly address. So the density number is competitive today. But the moving target is still moving. And TSMC is moving with EUV, with better thermal management, with a supply chain that includes the most advanced materials and tools on Earth. Huawei is matching them on one metric, transistor density, while still lagging on absolute process maturity, on power efficiency per transistor, and on the breadth of the software ecosystem. Second, the manufacturing reality. SMIC is producing the Kirin 2026 using DUV multi-patterning. That means 4, 5, possibly 6 exposure steps to define a single layer. Each additional step adds cost, adds time, and reduces yield. The per-wafer cost of a multi-patterning process is significantly higher than a single-patterning EUV process at the same node. That means Huawei is paying a sanctions tax on every chip. The chip works, the chip ships, but it costs more to make than its TSMC equivalent. Third, the software ecosystem. A chip without software is a rock. And Huawei's Harmony OS, while growing rapidly, is still a fraction of Android and iOS in terms of app availability, developer familiarity, and global reach. The Kirin 2026 is going into a phone that runs Harmony OS. And Harmony OS is still building its developer ecosystem, its app library, its enterprise adoption. The chip is world-class. The platform around it is still catching up. None of this erases what the engineering has already proven. It simply marks the distance between a breakthrough and a complete ecosystem. The density is matched. The architecture works. The chip ships. The rest is yield, cost, software, and time. And those are exactly the variables that compound in your favor when you have 110,000 researchers and a national mandate behind you. Which brings us back to the bigger picture this whole story has been building toward. Because this is not really about a phone chip. It is about the end of a 60-year monopoly on the rules of semiconductor progress. Moore's Law was not just a technical observation. It was a geopolitical architecture. The country that controlled the shrinking controlled the future. And the shrinking required EUV. And EUV required ASML. And ASML required Western permission. That was the pipeline. That was the kill switch. And the kill switch was flipped. And the response was not to build a different pipeline. The response was to declare that the pipeline itself was the wrong abstraction. that you do not need to shrink. You can fold. You do not need EUV. You can multi-pattern. You do not need cadence. You can build your own tools. You do not need permission. You need architecture. The Tau scaling law is not just a chip design principle. It is a declaration of independence from a technology tree that was designed to have one trunk and one gatekeeper. And once that declaration is made, once a second path is proven, shipped, and sold to consumers, the monopoly is over. Not because the first path stops working, but because the assumption that it was the only path is dead. And here is what makes this irreversible. You cannot undesign an architecture. You cannot unpresent a scaling law. You cannot unship a chip that works. Every Kirin 2026 that leaves the factory is one more data point proving that the sanctions architecture failed. Every developer who writes for Harmony OS is one more node in a parallel ecosystem. Every engineer who learns LogicFolding design flows is one more person who does not need the Western toolchain. The world that ran on Moore's law did not announce its own ending. It just started losing ground to a different law, written in a different language, by engineers who were told they could not compete. So here is the question I want to leave you with, and I genuinely want your answer in the comments. In a world with two scaling laws, Moore's law, driven by shrinking, controlled by the Western coalition, and Tau scaling, driven by architecture, driven by China, which one do you think produces the more powerful AI chips over the next decade? The one with the better lithography, or the one with the more desperate engineers? Drop your answer below. I read every single one, and if you want to be here for the next time a 60-year monopoly gets broken by a reframe, hit subscribe. We are building something here, and the next few years are going to be the most consequential decade in the history of computing. You are going to want a front row seat. I'll see you in the next one.